This is a video about the commercial applications of electrochemical cells. If you need more general information about redox reactions, half equations and electrode potentials, then check out the rest of the A-level chemistry playlist. Electrochemical cells can be split up into three types. Firstly, we can divide them into chemical cells and fuel cells, and then chemical cells can be divided into ones that you can recharge, or sometimes they're called reversible cells, and ones that you can't recharge, so they're irreversible cells. In a chemical cell, the chemical reaction is going to stop as soon as one of the reactants has been used up. And then if it's a rechargeable cell, you apply a big voltage to reverse the reaction and turn the products back into reactants so that you can use it again. Sometimes that's not possible, usually because one of the products has then gone on to be used for something else or made into something else and it's not available anymore. And that's why there are certain cells that you can recharge and certain cells that you can't. In contrast to that, a fuel cell doesn't ever stop working because you're constantly supplying the reactants, and so they're never going to run out in the first place. When you encounter an exam question that discusses chemical cells or fuel cells, it's almost certainly going to incorporate some of the things that we've discussed in earlier videos. So pause this one quickly and just make sure that you can define what we mean by a reducing agent and write the conventional representation for this cell. So hopefully you managed to write down that a reducing agent is an electron donor, and the cell for measuring the standard potential, we're going to be measuring it against the standard hydrogen electrode. So we've got platinum phase boundary, hydrogen gas phase boundary, hydrogen that's going to come from an acid, so it's aqueous. Then we've got our double line for the salt bridge, and then we've got our zinc ions, and then finally our solid zinc, because as you know, the most oxidized species is always going to go nearest to the salt bridge. If you're sitting the AQA A-level Chemistry exams, then there aren't named examples of non-rechargeable cells that you need to know about, but these ones come up with a fair degree of regularity, so they're worth you being familiar with. Firstly, we've got the classic Daniell cell, which we've already met. So this is our one that's zinc with zinc sulfate and copper with copper sulfate, but that's just not practical for a portable battery because you've got liquids that will be sloshing around and it would just be madness. So be aware that that is an example of a non-rechargeable cell, but it's not one that you're going to find in your CD player or whatever. This next example is one that you will have met many times in your life. So if you go to the supermarket and you buy a really cheap pack of batteries, what you get is a zinc carbon cell, which is pictured over here on the left. So the first thing we notice is that it's got this zinc case around the outside, and that's actually functioning as the anode. So as you can see here in our half equation, over time that nice solid zinc that's keeping everything up together is going to be losing electrons and turning into zinc ions. And that's why if you have one of these cheap batteries for long enough, it will split and it will start to leak and let the ammonium chloride out, which is kind of a bad thing because it's really corrosive and will burn you, just because the zinc is getting used up because it's getting oxidized. So that's our anode, and then our cathode is this central chamber here that contains manganese dioxide and powdered carbon all mixed up together, and then to allow that to conduct into it is a carbon rod, a graphite rod, and on top we've got a sort of metal lid. So if you look at the top of a battery and there's a dimple, that's where the carbon rod is. And then inside the rest of the cell is our ammonium chloride electrolyte, so it's sort of a paste and water, and that's sort of split up from the zinc casing by this porous membrane, which is going to allow ions to move through, but not anything else. Now, over time, what's going to happen at the cathode is this second half equation here, and initially this actually forms hydrogen, it forms hydrogen gas, but very, very quickly the manganese dioxide oxidizes that hydrogen gas to be water. And this is why this cell isn't going to be rechargeable, because in order to recharge it we'd have to reverse the reactions, so we'd have to turn the products back into the reactants, but we can't because the hydrogen has already gone on and been turned into the water, and so because it's water it now can't go back the way, so therefore we can't reverse this reaction. Now sometimes you're going to see this cell be slightly modified, so instead of using ammonium chloride they actually use zinc chloride, and this tends to be used because it generates a higher current and because it's a longer life cell. Just like an exam question that deals with redox chemical reactions, you need to be able to take two half equations and put them together to produce an ionic equation for the overall process. And then you also need to be able to calculate the electromotive force of that cell. We've mentioned before that in a proper A-level question you're probably going to have a table with 5 or 6 half equations and need to pull out the relevant ones, but here, just to be kind, we've just given you these two. So my first job is to look at these two half equations and figure out which one's going to go in the forward direction and which one is going to go in the reverse direction, because right now these are obviously both written as reduction potentials, but one of these reactions is actually going to have to be oxidation. So the rule is that the more positive E0 value, that reaction is going to go in the forward direction, and then the less positive one is the one I'm going to flip. So here it's nice and straightforward because the zinc potential is actually a negative number. It's obviously less positive. So that's the one that I'm going to flip over. So I've now got my, my manganese oxide equation proceeding in the forward direction as a reduction, and then my zinc is being oxidized instead. And what I immediately notice is that I have 2 electrons being produced when the zinc is oxidized, but in my first equation I only have 1 electron being used. So now my second step is to balance that first equation so that these work out. So now I have 2 electrons in my first equation to match the 2 in my second, and that means that when I put these together they're going to cancel out. So my final equation overall is going to look like this. And now to calculate the EMF, I'm going to take my second potential away from my first one. So I'm going to do positive 0.74, take away minus 0.76 to give me an overall potential difference of plus 1.50. And remember, it doesn't matter that I've needed to balance the equation and multiply everything by 2. That's not actually going to change the electrode potential. You may also find questions which refer to alkaline batteries. They were the named example of a non-rechargeable battery if you did AQA GCSE chemistry. And basically the only difference here is that instead of having an acidic electrolyte like ammonium chloride, you have an alkaline electrolyte like potassium hydroxide. So here's an example of a zinc alkaline cell, and I'm interested in an overall equation for the reaction between the zinc and the oxygen, the EMF of this cell, and also which electrode is which. So my oxygen is going to enter the cell through this air hole up here, and it's going to react with some of the water from this aqueous alkaline paste and also pick up some electrons. It's going to be reduced, and it's going to form some hydroxide ions. And then we've got this porous partition here, which is basically acting like a salt bridge, which ions are free to move through. And then down below it, we've got some zinc powder in an alkaline paste. So that's my zinc here. And then the alkaline paste obviously has hydroxide ions in it. So to make my overall equation, I'm going to be using the second half equation and also the fourth half equation. And actually, even before I look at the potentials, I know from this question that it's going to be zinc reacting with oxygen. So I know that it's going to be this fourth equation here that I need to flip over. But if I hadn't picked that up, I know that it's always the more negative equation which is reversed. And obviously negative 1.25 is more negative than negative 0.44. So it's this fourth half equation that is going to be flipped over. So if we do this, then here are our 2 half equations. And the next thing that I notice is that my electrons aren't balanced. I've got 4 electrons being used in the reduction process that is happening in the first equation, but I've only got 2 electrons being released in the oxidation process that's happening in the second equation. So I need these numbers to balance, otherwise they won't cancel out. And so everything in that second equation is now going to be multiplied by 2. So now that I've added some coefficients, the electrons balance out, but also now so do the hydroxide ions and the water molecules, and I don't need them on both sides of the equation. So before I put them together, I'm just going to cross all of those out, and what I'm left with is 1 mole of oxygen reacting with 2 moles of zinc to make 2 moles of zinc oxide. So now to calculate the EMF of the cell, we're always going to do the more positive value subtracting the more negative value. So we have negative 0.44 take away negative 1.25, which gives me a potential of positive 0.81 volts. And then finally, thinking about which electrode is which. Remember, your anode is going to be the site of oxidation and your cathode is going to be the site of reduction. So we've got our oxygen up here is gaining electrons, reduction is gain, so that's reduction. So the oxygen needs to be in contact with the cathode. So our lid up here is going to function as the cathode. It's going to be the positive electrode. And then the case down here is going to be our negative electrode, our anode, because the zinc is being oxidized, it's losing electrons, and so when those electrons are absorbed by the electrode, it's going to make it negative overall. So next up, we've got two examples of rechargeable cells, and it's probably worth pointing out that the way that you recharge a cell is that you apply an external voltage that is bigger than the voltage that that cell was making when it was discharging, when it was just working normally. And that's literally going to cause the chemical reaction to run in reverse and the products to turn back into the reactants. So if you get asked for the half equation during the charging process, you take the half equation for that particular electrode while it's discharging, just doing its normal thing, and you literally just flip it over. So these lead acid cells are really, really common. They're the basis of car batteries. And usually the way that it works is that you have 6 of them wired together in series to give you an overall battery with a potential difference of about 12 volts. So the way it works is that you've got 2 sheets of lead here, and the negative one is just lead on its own, and then the positive electrode is coated in lead oxide. And those 2 sheets are dipped into sulfuric acid. So if you ever hear sulfuric acid referred to as battery acid, that's why. And so at our negative electrode, obviously our anode, we've got oxidation happening. So we've got the loss of 2 electrons from the lead when it reacts with the sulfate ions from the sulfuric acid. And then our positive electrode, we're going to be picking up those electrons being reduced. So this is our cathode, and so the lead oxide is reduced with 4 hydrogen ions and a sulfate ion to make some lead sulfate and also some water. And so if we put all those together and we cancel out the spare electrons, then what we're left with is this. One last thing that's worth pointing out here, because it is a common error when it comes to questions about cells and batteries and fuel cells and things, is that because this first equation here is already it's already been flipped over to make it an oxidation potential rather than a reduction potential, the sign here has already been changed. Okay, so both of these reactions are now going to proceed in the forward direction as they're written, and that means when I come to work out the electromotive force of this cell, I'm actually going to be adding them together, not subtracting them. Another example of a cell that you've almost certainly met in your everyday life is a lithium cell. Now, there are actually loads of different kinds of lithium cell, so don't go getting confused if you're reading Wikipedia or whatever. We're only interested in this one particular variety because that's the one that AQA named in your specification, and they actually give you the half equations for the different electrodes, and so you're expected to have those memorised. Don't think that they're going to give them to you in the exam. So, important things to know about lithium cells. One is that they're very light because lithium is obviously very low density. Second thing is that they actually have a solid electrolyte, which is made of a polymer. So that's going to mean that there's no leakage because you don't have any liquids to come out. And also you're not going to risk a reaction between lithium and an aqueous electrolyte because there isn't any water there. The electrodes are made out of lithium cobalt oxide, that's your positive electrode, and then carbon, which is your negative electrode, and they're sandwiched together with solid polymer in between. So the lithium ions are free to move around. So the half equations you need to know are these. And this is the negative electrode on top. It's negative because lithium is being oxidized, so I've already flipped this this equation over for you, and so these electrons are going to be there's like a surplus, so that's why that electrode is going to be negative, and that's your anode because there's oxidation happening. And then at your cathode we're going to have reduction, where the lithium ions gain some electrons, and overall we make this lithium cobalt oxide. And so if we put those electrode potentials together, like we mentioned on the last slide, because I've sort of said these are the half equations that are happening at the electrodes, they're not both reduction potentials. The top one has already been flipped, so rather than taking them away, I just add them together to find out that this lithium cell is going to have a voltage of 4. Here are some examples of the kinds of things that they could ask you about lithium cells. So just like with all these cells, you could be asked to write an equation for the cell discharging. So just make sure if that happens, you know whether the 2 equations that you already have, the 2 half equations, whether they're both written as reduction potentials, in which case one of them needs flipping, or whether they're written as the equations that happen at each electrode, in which case you just add them together. So we get an overall equation that looks a bit like that. You could be asked to identify which species has undergone a change in oxidation state. So remember, unless there's a peroxide involved, oxygen is always going to be -2, and our lithium from group 1 is going to be +1. So actually, even without working out the oxidation state of cobalt, I know it's going to be the cobalt. But then if my next question asks me what the oxidation states are, well, in this left-hand example, I've got no overall charge, so that means that cobalt's going to be +4, but in this right-hand ion, I've got a charge of -1, so the cobalt is only going to be +3. And then for our last question, we want a half equation for what's going on at the cathode during charging. So remember, cathode is going to be reduction. So we're going to have electrons being gained. So what's going to happen there is the reversal of this process here. My lithium ion is going to gain some electrons and turn back into lithium atoms. On a final note about rechargeable cells, the advantages of using them are twofold. One is that disposing of cells is hard because they often contain toxic chemicals. But those electrolytes also contain metals that are in short supply. So by recharging and reusing the same cells, we can minimise the need for mining more of these. So we've spent 15 minutes talking about chemical cells, where you start out with a finite amount of each of your reactants, and they're reacting together, and then when one of them runs out, the cell stops working, and you have to decide whether it's rechargeable or whether you're just going to dispose of it. Now, in contrast to that, the way that a fuel cell works is that it's being constantly supplied with a fuel, usually hydrogen, sometimes methanol, and also air or pure oxygen. And then that means that the cell is able to just keep on working continuously. So within that cell, the fuel is oxidised electrochemically. So what that means is that rather than it directly reacting with oxygen, kind of the overall reaction is the same as if it were just being combusted, but what's actually happening is that the fuel is being used to make ions, and then the electrons are moving, and then the ions are joining together. And the advantage of this is that if you were just combusting it, you'd be losing a huge amount of energy as heat. But when you're doing this electrochemically, that doesn't happen. So from that point of view, it's much, much more efficient. If you did triple science for GCSE and you met fuel cells, you probably met the hydrogen fuel cell. So we've got a pipe that allows hydrogen to be pumped in, and then some of that hydrogen is going to undergo oxidation to produce some hydrogen ions and some electrons. So the electrons are going to be carried away by the anode, and the hydrogen ions are going to carry on through a porous membrane into the electrolyte. And any leftover hydrogen that wasn't oxidised is just going to be pumped out again. Meanwhile, over at the cathode side of things, some air or possibly some pure oxygen is being pumped in, and this oxygen is going to react with some water and be reduced and pick up some electrons to make some hydroxide ions. And what's going to end up happening is that they then join together with the hydrogen ions to make water, and the water is going to be released along with any leftover air that wasn't used. So we end up with an overall equation that is just hydrogen plus oxygen reacts to make water. And we've also got a wire up here that the electrons are actually travelling through to get from the anode to the cathode. Hydrogen fuel cells are a prime opportunity for the exam board to ask you to compare and contrast or evaluate. So it could be comparing and contrasting them with rechargeable chemical cells like I've done here, but equally it could be looking at comparing it to direct combustion of hydrogen, in which case you really want to be talking about the huge losses of heat when you do that, and also the fact that it's probably a bit more dangerous. So first thing, any kind of fuel cell is a continuous process. You're continually supplying fuel, you're continually supplying oxygen. There's never any point where it runs out. Whereas any kind of chemical cell is going to run out. It's a batch process. You start out with a finite amount of reactants, and when they're gone, they're gone. Linked to that, because a fuel cell is just running continuously, there isn't any reduction in efficiency. But with a rechargeable cell, each time you charge it, it's going to store slightly less energy. And there's variation between different kinds of rechargeable cell as to how much they manage to retain and how many times you can recharge them before it's just not worth doing it anymore. But compared to a continuous process like a fuel cell, there is going to be a reduction in efficiency. Now, thinking in terms of waste products, the great thing about hydrogen is that when you burn it or when you electrochemically oxidise it in a fuel cell, you don't really have any nasty waste products. You certainly don't have any carbon dioxide like you would if you were, I don't know, burning methane. But basically your one waste product is pure water. Now, when you think about those rechargeable batteries, part of the drive for developing rechargeable batteries is that lots of them have really nasty chemicals in them. So the waste products may be toxic when it's time to finally get rid of them. Now, one thing to be aware of is that hydrogen is highly, highly explosive, which is not great. So, you know, if you haven't heard of the Hindenburg disaster, look it up. Whereas for rechargeable batteries, although you're going to have some sort of toxic waste products and things, you're not going to have anything that can directly blow up in your face. Linked to this in a second, we're going to look at other things you can put in a fuel cell apart from hydrogen. But yeah, we'll get to that in a second. And then the other thing is that fuel cells have a relatively low potential difference. So therefore, you're not really going to be able to use one single cell on its own. You've got to join several together to make a battery. Whereas typically your chemical cells are able to produce a larger potential difference, and you could use it as just an individual cell. Just before we get to alternatives for hydrogen as a fuel for fuel cells, pause the video and make sure you're okay answering these. So in a hydrogen fuel cell, you've got hydrogen splitting apart to make hydrogen ions and 4 electrons. And then on the other side of the fuel cell, you've got oxygen together with some water picking up those electrons to make hydroxide ions. Those hydroxide ions are then going to go on to join up with the hydrogen ions to make water, which is our waste product. But initially, this is the reaction that's actually happening. So basically, hydrogen produces electrons and oxygen accepts those electrons, and that's what causes a current to flow. The fuel cell doesn't need to be recharged because hydrogen is just being continuously supplied to it, along with oxygen to oxidise that hydrogen. The major hazard is that hydrogen is highly, highly explosive. And finally, our conventional representation, we're going to need some platinum electrodes. So you've got your single lines for your phase boundaries, your most oxidised species nearest to the salt bridge in the middle, and platinum electrodes on either side. Now, hydrogen fuel cells probably sound like a great idea, really green, really good for the environment because there's no carbon dioxide, pure water is the only waste product. 2 small problems. 1, hydrogen, highly explosive, really very quite dangerous. Also, where do you get the hydrogen from? Well, most of it actually comes from methane, so a fossil fuel that we are running out of. Alternatively, you could produce that hydrogen by electrolysing water, but then you need electricity. And where do we get the electricity from? Well, in the UK, mainly by burning fossil fuels. So we're kind of back to square one. We've got a really dangerous fuel that is actually not great for the environment in terms of how we get it. So there are alternatives you can use. And one example of an alternative is methanol. So first thing going in methanol's favour is that it's much easier to store. Even though it's still flammable, it's not explosive. Secondly, you can manufacture it by fermenting it. So if you take some maize or some rice and you ferment it down, you can produce an alcohol, and then you can sort of distill that off. So that's obviously an advantage because we're running out of fossil fuels. There are some ethical considerations there. The whole, if there isn't enough food in the world, then is it really okay for us to take some of that food and use it to produce fuel? But in terms of how good for the environment it is, much, much better than just using the fossil fuels, burning the fossil fuels to produce electricity to do electrolysis. Also, because it's a liquid, it's got a higher hydrogen density. So each methanol molecule may have a carbon atom and an oxygen atom in there, but because the molecules are packed much, much closer together in the same amount of space, I have far more hydrogen. So from that point of view, it's much more space efficient. Finally, here are some half equations just to show you how it's done. So we've got the methanol and the water producing carbon dioxide, 6 electrons and 6 hydrogen ions. And then in the second equation, we've had to double up here, but we've got 12 hydrogen ions, 12 electrons, and some oxygen producing water. So overall, if I were to balance those and make them cancel out, then what I'd be producing is carbon dioxide and water. Thanks for watching. I hope you found that useful. Don't forget to subscribe.